Our research is an exploration of neuroplasticity and its control of a high-functionality prosthetic using support vector machines. Throughout our background research, we've looked into various different types of prosthetics and control systems. Particularly, we've looked at EMG-based prosthetics that use electromyography, reading the electrical signals based on muscle activity to control prosthetics with a certain number of actuators to create different grip types. However, this method of prosthetic control seems inadequate because the amount of information that you get from muscle contractions and the limited amount of muscles doesn't give you enough information to properly control a prosthetic and give you that high functionality and capability. So in our research, we have looked into support vector machines for classification of 7 different directional based feature vectors based on signal identities. And we've used this in series with a mechanical design for a prosthetic, an analog spherical encoder, which essentially maps every point around the sphere to a certain grip type. And using the classification of EEG signals using a support vector machine, this controls the directional axes of the sphere-based mechanical control.
For our EEG data collection, we use the International 1020 system to place electrodes using a standardized measure. The green highlighted circles in Figure 1 represent the areas of interest that we probed that were in relation to our investigation.
We also probed specific areas for high resolution in 1020 system, modifying it to specifically look at the M1 motor cortex, the prefrontal motor cortex, and the ventral premotor cortex. And gamma signals are 60 hertz, which are most indicative of active signals in the motor for motor commands. So we used a combination of frequency features, power features, and power spectral density features in order to build our support vector machine features.
For the engineering aspect of the methodology, we used a joint of 3 degrees of freedom to trace a surface of a sphere. By tracing the surface of a sphere with 3 degrees of freedom, we were allowed to have 3 motors and allow for more rotational freedom. And on the sphere, we connected 4 hydraulic cylinders using a bracket. For the data collection, we used the International 1020 system to place all the electrodes and mediated the placement with electrolyte gel. We repeated these steps for 3 more electrode placements. And for the experimental procedure, we had various rest trials to ensure sufficient data for the inactive brain signals, and we used various types of grip forces to ensure lots of data for all types of mobility for the hand.
Yeah, isometric contraction was used for the participants, providing very strong muscle commands coming from the brain. And in best practices for machine learning, each class type, one of each 7 different class types, we mounted the same amount of data for, so as not to overfit our support vector machine on one class of data. Here you can see a diagram of the prosthetic. On the left side of it, around the sphere, is the analog spherical encoder. You can see based on the yaw, pitch, and roll transformations done on a sphere, those 3 axes of rotational freedom can move these hydraulic cylinders on the top to any point of the sphere. And by doing this, they lengthen and contract in various ways. And this reflects in the hand in different grip types. So essentially, every single point on the sphere is a different grip type. And the support vector machine's classifications help navigate these points and do transformations on the sphere to produce different grip types.
This is a top-down view of the sphere and the 4 hydraulic cylinders connected to it. This was taken during coupling, where we connected the hydraulic cylinders to the brackets and then to the sphere for connection.
Here's a side view of the prototype of the analog spherical encoder with the hydraulics clearly viewed on the left.
By simulating a 16-channel signal, we produced 48 data points, and when we inputted these into the support vector machine, we extracted features such as rhythm energy ratios, power density spectrum, wavelength, and frequency bands. Each of these features highlight key aspects of our EEG data, and they allow for the accurate distinction between active and inactive brain signals.
Here's a top-down view of the analog spherical encoder with a output piston seen in front.
With a 95% accuracy using polynomial kernel and a 92% accuracy using sigmoid-based kernel, we can conclude that our features are viable in relation to our data. And it was all of these accuracy rates were constructed using 16 channels.
And here you can visualize those 16 channels for the power over frequency. So this is a example of a trial for power frequency graphs over 5 seconds. And this is a active trial where you can see over certain areas of the scalp, there are 20 hertz inhibitory signals, but in the region of concern, there is a high 60 hertz spike. And you can see all of these signals collated at the very bottom graph.
Based on our research and our investigation, we can conclude that machine learning-based EEG data classification allows for the best fitted control of a prosthetic device such as a hand. Through building our own prosthetic hand and collecting EEG data, we were able to create an optimized mechanical system that allowed for high control of the prosthetic hand. However, with many limitations such as the PCA reduction technique, time restraints, and lack of resources, some of our key data may have been lost, and for this reason, we recommend future research to validate our findings.
Thank you.
Thank you.